Chapter 9. In this chapter, I will talk about electrons in atoms and the periodic table. Then let's start chapter 9 by talking about the model of the atom. Then atom is the smallest part of an element, and it contains a small nucleus. Nucleus is the densest part of the atom. It contains protons that are positively charged, and it also contains neutrons that are no charge at all. Right outside the nucleus is where the electrons are. Electrons are negatively charged species, and electrons, they contribute to the size of the atom, whereas the nucleus contributes to the mass of the atom. Then, as discussed before, electrons, in comparison to protons and neutrons, are almost massless. Now let's talk about electromagnetic radiations. These are a form of energy that's being transmitted by light. Then electromagnetic radiations are a form of energy. Let me highlight that. Okay, it's kind of the energy of light. And if you look at this diagram, as you could see here, it is ordered by terms of increasing the wavelength. Then as you could see, gamma rays, they have the shortest wavelength, whereas radio waves have the longest wavelength. You need to memorize the order of these electromagnetic radiation, either in terms of increasing wavelength or decreasing wavelength. It doesn't matter. But going from the shortest wavelengths, which are gamma rays, next one is X-ray, and then it's UV light, then visible light, infrared, which is also known as IR, and microwaves, and the longest are radio waves. Okay. Now let's talk about properties of light. Light are also a form of electromagnetic radiation. Okay. Light is also a type of energy. Okay. And it travels at the speed of 3.0 times 10 to the power of 8 meter per second in space. This is a constant value for the speed of light in space. You don't need to memorize this number. If you need it, it will be always given. Now let's continue with the properties of light. The first thing is wavelength. Then if you recall 2 slides before, I mentioned wavelength. Wavelength is the distance between 2 adjacent wave crests. Then as you could see here and here, these are one wave crest next to each other. Okay, and the distance between 2 adjacent wave crests is called a wavelength. Okay. The SI unit for wavelength is meter. But since wavelength is so little, so small, the common unit is usually reported in nanometer. Okay, that's a common unit because it's so small. But the SI unit for it is in meter. It's just length. What's the SI unit for length? Meter. The way that we show wavelength is in a form of lambda, as you could see here. It's like an upside down V with a tail on it. Okay, that's lambda, stands for wavelength, and the SI unit for wavelength is meter, but the common unit is nanometer because they're so small. Next one, let's talk about frequency. Okay, frequency are the number of waves per second. Okay, then if you imagine a point in space, then by frequency you want to know how many times that wave passes that specific point in 1 second. Okay, that is why the unit for frequency is per second. Okay, we show frequency as nu. It's like an italic version of V. Okay, it's like a nu, and the SI unit for it is per second. Okay, then if you look at this equation, then C is a constant. It's the speed of light, which is a constant value. Let me change my color so that it might be visible. Okay, nu is the frequency, and lambda is wavelength. Okay, then C is the speed of light. The speed of light is meter per second, wavelength is meter, and frequency is per second, 1 over s, or s to the power of -1. Okay, again, this equation, you don't need to know this equation. If you need it, it will be provided to you, and you also do not need to know the number or the value for the speed of light. But one thing that you have to know is, what does the C stand for? Speed of the light. Lambda stands for wavelength, and nu stands for frequency. And you have to know this SI unit for each of these variables. Now, energy is either directly or indirectly associated with both the frequency and wavelength. Okay, then if you look at this equation, okay, which is energy is equal to, let me write it down one more time here. Energy is equal to Planck constant times frequency. Okay, and from the previous page, you know that the speed of light is equal to frequency times wavelength. Then what we're going to do, we're going to solve this equation in terms of wavelength, which is speed of the light over, in terms of frequency, which is the speed of light divided by wavelength. Now the next thing I'm going to do, I'm going to substitute 2 into 1. That means I'm going to rewrite equation 1 in terms of frequency. Okay, then if you do that, the energy will be equal to the Planck constant times the speed of light divided by lambda. Okay, what you could say is that both the Planck constant and the speed of light are constant, I just give it a number 1, just because it's constant, and it's divided by wavelength. Then as you could see here, the energy of the light is indirectly proportional to wavelength, whereas it's directly proportional to frequency. Okay? Why is it directly proportional to frequency? Because when you look at this equation, the energy of the light is equal to h is the Planck constant. I just give it a number 1, and nu is frequency. Then as you could see here, based on this equation, the energy of the light is directly proportional to frequency, whereas it's indirectly proportional to wavelength. Okay. Also, if I go back to my previous slide, if you look here, let me write it here, C is equal to lambda frequency. Then if the speed of the light, which is a constant, I give it a value 1, it will be equal to lambda times mu, and nu is equal to 1 over lambda. Then what you could see here, again, the frequency is indirectly proportional to wavelength. What that means is that if you increase the frequency, the wavelength decreases. And the same applies to the next page. That means energy is directly proportional to frequency. That means if you increase the energy, frequency increases, and if you decrease the energy, frequency decreases. Whereas for wavelength, if you increase the energy, the wavelength decreases, and if you decrease the energy, the wavelength increases. Then as you could see, the energy is directly proportional to frequency and is indirectly proportional to wavelength. And also between wavelength and frequency, they're also indirectly proportional. Now let's go back to this slide. All right, the electromagnetic radiation. Then as you could see here, this number for gamma rays, as you could see here, it has the shortest wavelength. Let me change my color. Gamma rays, so that you can see it. Gamma rays has the shortest, okay, and it has the shortest wavelength. But since wavelength and energy are indirectly proportional, then it has largest energy and frequency. Okay? And the same thing applies to radio waves. Radio waves have the longest wavelength, which make it to be the smallest energy and frequency. Okay? Then I might ask you to put these in the order of increasing energy, decreasing energy, increasing frequency, decreasing frequency, or either increasing or decreasing wavelength. Then you don't need to memorize all of it. Okay? You just memorize it in order of increasing or decreasing either one of these variables. Okay? And then you could do it for the other ones, since wavelength is indirectly proportional to energy and frequency. Right? And that's why God forbid, if somebody gets cancer, they are treated with gamma rays because they are very high energy particles. Okay, you're not going to get treated with radio waves, okay, but they will be treated with gamma rays because they have the shortest wavelength but highest energy. Now, let's continue talking about colors of light. Okay, if you pass a light through a prism, it will split into a series of visible light colors. Okay, and those colors are red. Again, let me change. R is red, O is orange, Y is yellow, G is green, B is blue, I is indigo, and V is violet. Okay. These are the colors of visible light. And also, again, as you could see here, it is written in an order. And that order is decreasing wavelength. Okay? Then as you could see here, based on this diagram, violet has the shortest, wavelength, whereas red has the longest wavelength. Then since red has the longest wavelength, it will have the smallest energy and it will have the smallest frequency. Whereas violet has the shortest wavelength, it will have the largest energy and the largest frequency. Then one more time. Wavelength is indirectly proportional to energy and frequency. Then when we have a longest wavelength, we will have shortest or smallest frequency and energy, and vice versa. Okay. Then again, you have to remember the order of these visible colors in terms of increasing the wavelength or decreasing wavelength. And I might ask you for the wavelength, energy, or frequency. Then based on the relationship between these three variables, you should be able to answer the question accordingly. Another way of memorizing it, which I've always done, is ROIC BIV. Just memorize it this way, ROIC BIV. Then you will know which one is which. That's a little hint. Now, let's talk about the emission of the light. Okay? Then atom can give off light. Okay? Then how can they give off light? In order for an atom to be able to give off light, it has to gain some energy. Okay? Remember, light is a form of energy, is an energy. Then it has to gain energy so that it could release the energy. Okay? Then in order for light to be able to release energy, first it has to gain the energy, and once it gains the energy, it becomes excited. Okay? It becomes excited. It's like giving a kid a box of chocolate. Once they eat it all, it's energy, they become excited. And then that energy that they have gained, it will released. And how does it release? In a form of photon. Okay? Photon is just light. Okay? Photon is light. Okay? Remember, the smallest unit of an element is an atom. The same thing, the smallest unit of light is photons. Okay? Photons are particles of light. Okay? Then one more time, an atom, it gets the energy, it absorbs the energy, becomes excited, and then it eventually releases the energy, and it releases that energy in the forms of light. Now let's talk about it in this diagram. Assume lithium atom. Okay, lithium atom, okay, before it gains energy, okay, on their own, without being excited, they are always at the lowest energy level, which we call it ground state energy. Ground state energy is the lowest energy level. Okay, that's the ground state energy. Okay, it's like that kid sitting, not doing anything, just minding his or her own business. Okay, then all the atoms like to be at the ground state. That's where they are the happiest most. But then what happens is that they receive energy. Okay, it's like giving candy to a kid. Then once they get the energy, they move from ground state to excited state. Now this is an excited state. Excited state, any state above ground state. Okay, any state above ground state. It's an excited state. Okay, then what happened here? The lithium atom, let me use my laser. The lithium atom right here was at its lowest energy level, which we call it ground state. That's where all the atoms are happiest the most. Then here, lithium atom, it absorbs the energy, okay, and it moves from ground state to a higher state, which we call it excited state. Okay, excited state is any state above the ground state. And as you could see in the picture, this shows an excited lithium atom. You see all this like wedges, the wedges, okay, or the wigglies, that shows an excited lithium atom. And eventually everything comes back down, right? That excited lithium atom has to come back to its ground state. Then once it comes back, or it goes back from an excited state to the ground state, it has to release the energy. Remember, by the law of conservation of energy, energy is neither recreated nor destroyed. Then the energy that lithium absorbs right here to go from ground state to excited state, once it goes back to the ground state, it releases that energy. Okay, and how does it release that energy? In the terms of light or photons. Okay, and for lithium atom, that light, the color of that light is red. When you do a light test for lithium atom, you will see it. If you dip in a rod and a lithium and then put it on a flame, the flame test for it will be red light. Okay, that's a flame test for lithium. Okay, then one more time, let's go over it one more time. Then what happens here is that the lithium atom is at the ground state. It's the lowest energy level, which that's where all the atoms are happiest. Then what happens? Lithium atom, it absorbs the energy and it moves from a ground state to excited state. Any state above the ground state is excited state. And then eventually that excited lithium has to come back down. And once it comes back down, it releases the energy, and it releases the energy in terms of light, and the color for it is red. Okay, that's why when we do a light test for lithium, flame test for lithium, it's red color. You should be able to explain everything that I just explained, and if I ask you to draw an energy diagram, that's what I want you guys to be able to do, to draw a simple energy diagram for emission of light. Just show me the ground state, excited state, and what happens to atom. Okay, you don't need to know the color of the lights that atoms emit once they go back down to ground state. If you need it, I will let you know, but you have to be able to explain this concept. Now let's talk about the hydrogen emission line. It's exactly the same concept. Okay, then as you could see here, hydrogen atom right here, let me change the color. What is it? It's at the ground state. Okay? It absorbs the energy and it moves from ground state to excited state. Okay? These are excited hydrogen atom, which we also can show it like that. Once it goes from ground state to excited state, it eventually come back down to the ground state. Okay? Then I'm going to show ground state as in GS, excited state. Now once that hydrogen atom is excited at the excited state, it will go back down to ground state and it releases the energy. Okay? Exactly the same concept. This is the kind of the emission line for hydrogen. Then hydrogen, what it is, let's draw it right here. This is hydrogen. Okay, at the ground state, it absorbs the energy and it goes up to excited state. That's an excited state hydrogen, and it will eventually come back down. And once it come back down, it releases the energy in terms of light. Okay. And this is what I've just been talking about. But as you could see in the next picture right here, everything is not as simple as just the diagram A. We call it A. A is just so simple. Hydrogen atom, it gains the energy, it moves from ground state to excited state, and then it goes back down. What is on diagram B is really what's happening. Okay. What is it? Is that we have only one ground state. One ground state. But what we could have one or more excited state. Okay? Then as you could see for hydrogen atom actually has 4 excited state. Okay, what I want you to understand, what I only want you to understand is that some atoms have more than one excited state, but you don't need to know how many excited state each atom has. Okay, that's all you need to know. Then if we could only have only one ground state, but we could have one or more excited state. And for hydrogen has 4 excited state. That's why you will see 4 different emission lines for hydrogen at different wavelengths. Okay, the wavelength for one of them is 410. Second one is 434 nanometer. Third one is 486 nanometer. And fourth one is 656 nanometer. You don't need to memorize these numbers at all. That's all I want you guys to understand, is that where these numbers are coming from is just from hydrogen atom, okay, going back down to the ground state. Okay, since hydrogen has 4 excited states, when you go back down, it has 4 emission lines. Okay, that's all I need to know. You don't need to know the colors, you don't need to know the numbers. That's the only thing you need to know, is that hydrogen has 4 emission lines. Why? Because it has 4 excited states. And you don't need to know how many excited states each atom has. Okay. Now, let's continue with hydrogen emission lines. Okay. One thing that you need to know is that emission lines for each atom is unique. If you're not told what that specific atom is, but you're told these are the emission lines for this atom, if you look at the literature, you can find out what that atom would be. Remember, we talked about density, how density is unique for each solution. It's kind of the same thing. Then each element has its own emission line, which is unique for each element. Okay, That's why we call it energy levels are quantized, okay? Because each atom has its own discrete energy level. That applies to hydrogen and applies to any other atoms, okay? Then energy levels of all atoms are quantized. That means each atom has its own energy level, or it has its own emission line. That's what it means by the fact that energy level for each atom is quantized. Okay, remember how density is unique for each solution? Same thing, energy lines for each atom is quantized. And this picture exactly explains the quantization of energy. If you look at this guy, what this guy is gonna do, this guy is gonna go and get that can of Pepsi. Then in order for this little guy to reach that can of Pepsi, as you could see here, it has to go through every single step, okay, to get that can of Pepsi. That's what we mean by the fact that that energy is quantized. That means for this guy to get to that can of Pepsi, you cannot just jump to step 5 and then go get it. Okay, it has to go from step 1 to step 2 to step 3 to step 4, step 5, step 6, and etc. That's the same. That's exactly the same thing when we talk about energy and the fact that energy level of all atoms are quantized. That means for energy levels, okay, to go from one step to another step, it has to go through all the steps. It cannot jump from step 1 to step 3. In order to get from step 1 to step 3, it has to go from step 1 to step 2, then to step 3. And the same thing when it wants to go back down, okay? In order to go back down, it goes from step, for example, step 4 to step 1. Then you cannot directly jump to 1 or go to 3 and 1. Then it has to go from 4 to 3 to 2 to 1. That's the definition of the fact that energy is quantized. That means you have to go through every single level, whether it's going up or when you're going back down. Now let's introduce you to the Bohr model of the atom. It was developed by It was developed by Niels Bohr. He was a Danish physicist, and he developed a simple model to explain the energy levels of electrons. Okay, he only talked about a simple model. Then based on Bohr's model of the atom, okay, energy level is quantized. Then if you look here, okay, these energy levels, which you can see it as N1, N2, N3, N4, N5, N6, these are the rows on the periodic table, which is row 1, row 2, row 3, row 4, row 5. Okay, then the lowest row, which is the one that's closest to the nucleus, as you could see here, okay, then the row that's closest to the nucleus is number 1, and the second closest is 2, and then etc. Okay, then so far we have 7 rows on the periodic table. The rows goes from left to right. Okay, we have 7 of them. Okay, that's why we have 7 rows on the periodic. We have 7 rows right here. Well, actually, we have to add one more. Okay, then for electron to move from energy level 1 to energy level 4, it has to go through energy level 2, then energy level 3, then reach to energy level 4. Okay, it cannot just jump from energy level 1 to energy level 4 because energy levels are quantized. Okay, even if it wants to go back down from 4 to 1, It has to go through 3, then back to 2, back to 1. It's just like that guy getting that can of Pepsi. It has to go through every single step. And electrons, again, have to go through every single energy level, okay? Now, electron, he also proposed that electron, they move in a circular orbit, okay? Then what it is that. Then he called each of these energy levels like an orbit, okay? And he said electrons are in these orbits around the nucleus, okay? And he also included that electrons, they move from a lower energy level to a higher energy level by absorbing energy, okay? And once they go back down, they release that energy. That's something we just learned, okay? Going from a ground state to excited state, and once they go back, they releases the energy. Then let's go over the Bohr model one more time. Then according to the Bohr model of the atoms, energy levels are quantized. That means for electrons to go from energy level 1 to energy level 5, it has to go through 1, 2, 3, 4, and 5. Even the same thing when it go back down. Then it has to go from 5 to 4 to 3 to 2 to 1. It cannot jump between the levels. He said electrons move in a circular orbit. Then he called each of these energy levels an orbit. And what he said is that the electrons are moved around the nucleus in an orbit. And he also added that electrons, they could jump or they could go from one energy level to another one by absorbing energy. And once they go back down, they release that energy, okay, in terms of light. And since energy levels are quantized, then each atom has its own unique emission line, as we discussed for hydrogen. Like it had 4 emission lines, and etc. All right. Now, the problem with the Bohr model was that it only worked for hydrogen. The Bohr model did not work for any other element, just for hydrogen. Why? Because hydrogen only has 1 electron. Okay, if you look at the periodic table, hydrogen has only 1 electron. And since it only had 1 electron, it only worked for hydrogen. But for all the other atoms that had 2 or more electrons, it did not work. Okay? The Bohr model was failed. These are the reason for it. One other thing that did not work, and it was against Bohr's model, was that electrons, they do not move in a circular orbit. They do not do that. Okay? That's why the Bohr's model was replaced by a more complicated and more detailed model, and it was called quantum mechanical or wave mechanical model. Okay? That's a new name for the model that replaced Bohr models of the atom. Based on the new model, which is the quantum mechanical model, number 1, the Bohr's orbit was replaced with orbitals. Okay? Instead of saying electrons, they move around the nucleus in a circular orbit, it was replaced with orbitals. Okay? Orbitals are different from orbits. Orbitals are the home of electrons. Okay? You have the highest probability of finding an electron at a time in an orbital. Okay? That's where you have the highest probability of finding electrons is in their orbitals. Orbitals are the home of electrons. Okay? Also, the new model gave a number and a letter for each orbital or orbitals. Okay? Then each orbital has a name and it has a letter. Okay, a letter and a number for each orbital depending on where on the energy level it is. Okay, then if this is the nucleus, okay, which has proton and neutron, this is energy level 1. I'm just gonna put that. I don't want this N and that N. They're two different things. That's our nucleus. Okay, that's energy level 1, energy level 2, energy level 3. Okay, then the lowest energy level to the nucleus, remember we call it energy level 1. Okay, and the orbital for it is S. Okay, 1s. Okay, why is it 1? Because it's in energy level 1. Why is it S? Because that's S is the only orbital that can be in energy level 1. Okay, and write down 1s. That 1, it's in energy level 1, where n is equal to 1, and that S, that's the name for the orbital that can only exist for in energy level 1. In energy level 1, we could only have S orbital. Okay, that's the only orbital that exists. Then as you could see here, then these energy levels are numbered. Okay, and the one that's closest to the nucleus is energy level 1, and then it's 2, 3, 4, 5, 6, 7, since they have 7 rows in the periodic table. You could call that N energy level or principal energy level. It's the same thing. You hear me call it all the time, energy level. It's the same thing. Okay, then energy level or the principal energy level is we show it as in lowercase n, and the one that's closest to the nucleus is energy level 1, and we go all the way to 7 because we have 7 rows on the periodic table. Now also, the higher the principal energy level, okay, the higher the energy of the orbital. That means if our principal energy level, if you compare the principal energy level 2 and 3, principal energy level 3 has higher energy, okay, than principal energy level 1. Okay, then as we go from principal energy level 1 to 2 to 3 to 4 to 5 to 6 to 7, the energy of the orbitals also increases. Okay, then the higher the principal energy level, the higher the energy of the orbital. Okay, they're directly proportional. Then as the principal energy level increases, the energy of the orbital also increases. All right, now remember I said each orbital has a number and a name. Okay, then we have principal energy level 1, principal energy level 2, principal energy level 3, principal energy level 4, principal energy level 5, 6, and 7. Okay, now what I'm going to do, I'm going to talk about each energy level. Okay, also one other thing is a good idea to indicate is that in each principal energy level we have a sub level. Okay, you see these? Then in principal energy level 1 we only have one sub level. In principal energy level 2 we have 2 sub levels. In principal energy level 3 we have 3 sub levels. In principal energy level 4 we have 4 sub levels. One thing that you want to know is that these principal energy levels have energy levels, and also the sub levels, okay, have their own energy level. Okay, then both the principal energy levels and the sub level, they have their own energy levels. Okay, that's important. Now let's talk about energy level 1. Then energy level 1 is the one that's the closest to the nucleus. It's the first row on the periodic table. Okay, this is energy level 1. If this is our nucleus, this is energy level 1. Okay, in energy level 1, we have s orbitals. An orbital is s orbital. That's in energy level 1. Okay, we have s orbitals. S orbitals, they look like spheres. Okay, it looks like a sphere. All right, and if you look at energy level 1 and energy level 2, okay, let's think about the x and y axis. Okay, x and y axis. If this is the s orbital for energy level 1, okay, which or also call it 1s, then if we want to think about the size of the energy level, okay, let's write it in white, the size of the energy level for s orbitals when we are talking about energy in energy level 2, okay, then the size of the s orbital will be larger in size. Okay, remember, as the principal energy level increases, the energy of the orbitals also increases, same as the size of the orbital. Then 1s orbital is smaller than 2s orbital. Okay, 2s orbital smaller than 3s orbital. Then in every single energy level, we have s orbital. Okay, we have s orbital in energy level 1, 2, 3, 4, 5, 6, 7. And as the energy level increases, the size of the s orbital increases. Okay, as you could see in this picture. Now, one other thing that I'm going to talk about is orbitals. How do we show orbitals? Okay, orbitals, some books show them like a little sphere. Some books show it like a little squares or boxes. Okay, that's how the books, different books, show them orbitals. Our textbooks show it in terms of boxes. That's why I'm going to stick to boxes. I think the online homework does this spheres. I'm not sure, but for our class, I'm gonna stick to boxes. Okay, the squares. It doesn't matter you do a sphere or square as long as it's like in either one. It's all cool. Now, in each orbital, okay, let me write it down. In each orbital, you could have the maximum of 2 electrons. That's the maximum number of electrons you could have in each orbital. It doesn't matter if it's an s or any other orbitals. You could have a maximum of 2 electrons in each orbitals. Okay? Then for s orbital, let me change the color. Then s orbital, okay, it's one box, and since you could have a maximum of 2 electrons, then in s, that's how many electrons you could have. Okay, that's a s electron. Okay, then now that we're talking about energy level 1, okay, in energy level 1 we have 1s2. Let me write it here so that let me change the color so that it does not get confused. Then in energy level 1 we only have 1s2. That one, because it's in energy level 1, that s, that's the orbital that exists in energy level 1, and that 2 is the number of electrons. Okay, electron. Okay, that's what 1s2 means. Then in energy level 1 we only have s orbital, and we could have a maximum of 2 electrons. Okay, then the maximum number of electrons in energy level 1 is 2. Okay, as you could see here. Then we could say that in let me write it here. The maximum number of electrons, maximum number of electrons in energy level 1 is 2. It's 2 electrons. Okay, 2 electrons. Let me put it here. Okay, all right. Now let's talk about energy level 2. Energy level 2, let's do energy level 2. That's our nucleus. This is energy level 1. Now we're talking about energy level 2. In energy level 2, okay, we have S and p orbitals. Those are the 2 orbitals that exist in energy level 2. Okay, then I've already talked about s orbitals. They are sphere shape. Okay, now what about p orbitals? P orbitals, or they look like dumbbells. Okay, that's a p orbital. Okay, this is a p orbital, this is a p orbital, and that's a p orbital. Then if you think about the axis on the periodic in an axis on a graph, okay, we have x, y, and z. Okay, let me change the color. Okay, if the orbital, the p orbital, sits on the x-axis, as you can see here, is px, p sub x. If it sits on the y-axis, okay, sorry, if it sits on the z-axis, it's p sub z, and if it sits on the y-axis, let me go with green, okay, it's p sub y. Okay, then depends on where it sits. Okay, then if we have px, py, pz. Okay, then if it sits on the x-axis, it's px. If it sits on the y-axis, is py. If it sits on the z-axis, is pz. Okay. Now, if we want to draw it in terms of orbitals, okay, they are 3 boxes joined together. It has to be joined together. If I ask you to draw the p orbitals, okay, if you put it 3 individual boxes, this is wrong. Okay, it cannot be 3 individual boxes. It has to be 3 boxes joined together. Okay, then it's what? This is p. Okay, then it could be px, py, pz. Then each of, not necessarily the first box is px, the second py, the third one pz. It could be any. We don't know which one it is. Okay, but we name it like px, py, pz. Like the first one could be py, the second one could be pz, and etc. As long as you know the p orbitals are 3 boxes joined together, okay, that's all I care about. Then if that p orbital sits on the y-axis, is py. On the z-axis, pz, and on the x-axis is px. Okay, now how many electrons will be in p orbital? Then remember, each box is 2 electrons. Sorry, I was going to say how many electrons in p orbitals. Then in each orbital is 2 electrons. Okay, now if you look here, since p, okay, is 3 orbitals next to each other, then in any p orbital we could have a maximum of 6 electrons. Okay, right? Then if you think about energy level 2, then we have s orbital 2, right? We have s and p. Then s is just one box, right? That's s. Okay, it's one box. Then in energy level 2, how many electrons do we have? We have 2 from s, and we have 2, 4, 6 from p. Okay, then 2 plus 6 is 8. Okay, then in energy level 2, right, okay, then the maximum electron in energy level 2 is 8 electrons. Okay, then 2 coming from s. Okay, 2 come from s and 6 come from p. Okay, then it's 2 plus 6, which is 8. The 2 is from s, the 6 is from p orbital. Okay, then how do we write these orbitals in energy level 2? Then in energy level 2, let me choose a different color. Okay, then it's going to be 2s2 y2s2 2p6. That's for energy level 2. Okay, then here we are talking about energy level 2. Let me put it in a box so that okay. Then in energy level 2, okay, we have 2s2 and 2p6. That's for energy level 2. Okay, then in energy level 2, we have s and p orbitals, and we could have a maximum of 8 electrons. Why? Because 2 coming from s and 6 coming from p, which makes it 8 electrons. Also, if you want to draw like a 2p and 3p p orbitals, just like s. Okay, let's talk about y, z, and x. Let's talk about px and py. Oh, sorry. For example, let's talk about this is okay. If this is 2px, then for 3px, okay, 3px will be larger in size. Okay. Remember one more time, the higher the principal energy level, the higher the energy and the larger in size. That's why, as you could see here, 3px is larger in size than 2px. Okay, then as the energy level increases, the size increases because we get further away from the nucleus. Okay, then this was energy level 2. Then in energy level 1, we only have s orbitals. The maximum number of electrons is 2, as you could see here. Okay, then in energy level 1, we have 1 s2. In energy level 2, we have s and p orbitals. We can have a maximum of 8 electrons. And we have 2s2 and 2p6. P orbitals are 3 orbitals or 3 boxes joined together, as you could see in this picture. Now, let's talk about energy level 3. Energy level 3, again, this is my nucleus. What I figured out is that these pens are not compatible with that program that I used to record my voice. That's why it jumps. If I disconnect the program, it's perfectly fine. And 1 and 2 and 3. And now I want to talk about energy level 3. Okay, in energy level 3, we have S, P, and d orbitals. Okay, that's in energy level 3. Then that's a new one, d orbitals. Okay, d orbitals are combination of s and p orbitals. Okay, then d orbitals, they are 5 orbitals joined together. Okay, 1, 2, 3, 4, 5. 3, 4, 5. That's a d orbital. Okay, then and we could have a maximum of 2 electrons in each orbital. Wow. Then as you could see, in any d orbital, we could have a maximum of 10 electrons. Okay, 2, 4, 6, 8, 10. Now, let's talk about the shape of the orbitals. This is the shape of the orbitals. As you could see, it's a combination of s and p orbitals. I do not ask you to be able to sketch the d orbitals, but if I give you one of the shapes, you have to recognize it's a d orbital. Okay, that's all I want you guys to know for d orbitals. Not to be able to sketch it, just to realize that this is a d orbital. Is, as you could see, it could be s and p like this one, or it could be 2p like these ones. Okay, these are all 2p's. Okay, could be s, p, or 2p's. Now, let's go back to d orbitals and in energy level 3. Then in energy level 3, we have d orbitals. We have s orbitals, and we have p orbitals. Okay, and this is s, and that's p. Then in s orbitals, we could have a maximum of 2 electrons, and in p, 6. Okay. Then as you could see here, what's the maximum number of electrons we could have in energy level 3? In energy level 3, we could have 2, 4, 6, 8, 10, 12, 14, 16, 18. Then in energy level 3, you could have a maximum of 18 electrons. Let's write it down. In energy level 3, we could have the maximum of 18 electrons. Okay, electrons. All right, now let me change the color. Then in energy level 3, okay, we have 3s2, 3p6, and 3d10. Okay, then these are the orbitals exist in energy level 3. Okay, and then it's 3s2. Why? Because we are talking about energy level 3, and in any s orbitals we could have a maximum of 2 electrons. Next one is 3p6. Then in energy, that 3 means we are in energy level 3. We are talking about p orbitals, and we could have a maximum of 6 electrons. Now in 3d10, that 3, that means we are in energy level 3. We're talking about d orbitals, and we could have a maximum of 10 electrons. Okay, then these are the orbitals that they exist in energy level 3. Okay, and as I said, we could have a maximum of 18 electrons. Let me include that. Why 18 electrons? We have 2 plus 6 plus 10. Okay, that's S, that's P, and that's D. Okay, let me make it smaller. All right, now let's talk about energy level 4. in energy level 4, what we have, okay, let me talk about energy level 4. Then this is my nucleus. That's where my protons and neutrons are. This is my energy level 1, energy level 2, energy level 3. Now energy level 4. Okay, as you could see in energy level 4, what orbitals do we have? Let me do red. Now I'm talking about energy level 4 or principal energy level 4. In principal energy level 4, we have S, P, D, and F orbitals. F orbitals. Now, how does the F looks like? F's orbitals are 7 boxes joined together. Okay, that's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and 7. Okay, oopsie. Sorry about that. Probably gonna go 1, 2, 3, 4, 5, 6. Let's make a 7. Okay, 7. This is the F orbital. Then F orbitals, there are 7 orbitals joined together. And what's the total number of electrons we could have? Is 14. Then in each orbital, we could have a maximum of 2. We have 7 orbitals. 7 times 2 is 14. Okay. Now, other than the F orbitals, they're a combination of S, P, D orbitals. I'm not going to discuss that. I even don't have a picture to show you guys. And you're not responsible to be able to recognize it. Okay. You have to be able to draw S and P orbitals. The shape of it. Remember, S is a sphere, P is double. D, you have to be able to recognize it. Okay. Which is a combination of S and P orbitals or 2P. Now, let's do D. 1, 2, 3, 4, 5. That's the D orbitals. Okay. Now let's continue with the P. Sorry, I ran out of space. P is 3 orbitals. Then all this S, P, D, F, these are all lowercase. Okay. You might show it as uppercase here, but they're all lowercase letters. And that's an S. Okay. Now, what's the total number of electrons we have in energy level 4? Okay. The maximum number of electrons in energy level 4 in energy level 4 energy level 4 is 32. Oops. Okay, let me erase that because I'm running out of space. In energy level 4 is 32 electrons. Okay, so why is it 32? Because it's 2 from S, 6 from P, 10 from D, and 14 from F, which makes it to 32. Okay, that one is from S. Let me change the color so that I can put them in. That's S, That's our P, that's a D, and that F. Okay? And that's the maximum number of electrons we could have in energy level 4. Then if I want to write it in energy level 4, we have 4s2, 4p6, 4d10, and 4f14. Okay? That's a 4f14. Okay? And these 4s, as you could see, represent the energy level, and those superscript 2, 6, 10, and 14 is the maximum number of electrons we could have. All right. Sorry about that. Let's change to pen. Now, in energy level 5, 6, and 7 is the same. Okay. Then in energy 5, 6, and 7, it's same as energy level 4. Okay, let me do my nucleus. 1, 2, 3, 4, 5, 6, and 7, right? This one, and is 1, 2, 3, 4, 5, 6, and 7. Okay, these are 7 energy levels. Then in energy level 5, 6, and 7, it's like energy level same as energy level 4. We have S, P, D, and F orbitals. Okay, then from energy level 4 to 7, we have all S, P, D, and F orbitals. Okay, now how would you know how many electrons do you have in each energy level? Okay, how many electrons in each energy level? What we're gonna use this formula, 2n2. N is our principal energy level. Okay, then for example, if it was in energy level 1, it would have been 2 times 1 to the power of 1, the power of 2, which is 2. Okay, then if n is 1, okay, then it would be, electron would be 2 times 1 to the power of 2, right? Which is 2. Okay, now let me change that. Okay, and if n is 2, the electron is going to be 2 times 2 to the power of 2. 2 to the power of 2 is 4. 4 times 2 is 8. Okay, now energy level, let's talk about energy level 5. Okay, is 2 times 5 to the power of 2, which is 50. Okay, and just use this formula so that you will know how many electrons in each energy level. Okay, now, okay, so one more time, let's talk about the S and P sublevels. Okay, then S is a sphere shape. Then as you could see, 1s is smaller in size than 2s, or in another word, as the principal energy level increases, the size of the s orbital also increases. Then s orbital, it's just one box. Okay, that's the s orbital. Now p orbitals, we have p, as you could see here, we're starting energy level 2. We have p orbitals. If that p orbital, it looks like a dumbbell. If it sits on y-axis, it's py. On x-axis is px. On z-axis is pz. And when you're naming the p orbitals, you don't need to write px, py, pz. Just the p orbital. Okay. Then as I'm doing here. Okay. This is the p orbitals. They are 3 boxes or orbitals joined together, and we could have a maximum of 6 electrons. in p orbitals. Okay. That's the d orbital. Starting energy level 3, we have sp and d orbitals, or d orbitals. D orbitals are the combination of, as you could see here, px and py orbitals, or they are the combination of a s and a p orbitals. Okay, as I told you guys, you don't need to be able to draw d orbitals. As long as you could remember the shape that represents a d orbital, I'm fine. Then d orbitals are let me change the color so that it's more clear. That's the yellow. Then d orbitals are 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. That's the d orbitals. They are 5 boxes joined together. Then d orbitals could have a maximum of 10 electrons. That's the d orbitals. And let's quickly go over the shells. Then in energy level 1, we only have the s orbitals. Okay. And in energy level 2, we have s and p orbitals. In energy level 3, we have spd. Energy level 4, spdf. 5, 6, and 7 is the same, spdf. And as you could see, we have s orbitals in every energy level. P starting energy level 2, D is starting energy level 3, and F is starting energy level 4. Then we also call these sublevel. SPDF is sublevels or subshells, and these are the energy level. Then, as I told you guys, energy levels have their own. These shells have their own energy level. Okay, like energy level 4 is higher than energy level 3, and etc. Also, these subshells have their own energy level. Okay. And then in order for you to know how many electron is in each energy level, use that equation 2 times n to the power of 2. You will know how many electrons is in each energy level. Now let's talk about two important principles. The first one is Pauli exclusion principle. By Pauli exclusion principle, what it says is that each orbital could hold the maximum of 2 electrons, and those 2 electrons have to be in opposite spin. You see this arrow? One is facing upward, one is facing downward. Okay. Why is that? Remember, similar charges repel. Then 2 electrons are negative charge. Okay, they repel each other. Then in order to be able to fit into the orbital, that's why they have to be opposite spin. Then if you do electrons, do the orbital like this for me, I will not give you any credit. Or if you do it like this, or if you do the 2 electrons like that, you will not receive anything at all. Then you have to make sure that the electrons in the orbital, they are opposite spin. That means the arrow, one facing up, the other one facing down. It doesn't matter. The first one we could face down. Okay. Like this one could face down, the other one could face up. It doesn't matter as long as you have one face up, one face down. One other thing that's not acceptable, you cannot do 2 lines. Okay, because I have to know which one is facing up, which one is facing down. Or you have to show me the Pauli exclusion principle. Okay, that's why we use this little thingies. Okay, then the order doesn't matter. Then this one is correct, this one is correct, but those 2 are incorrect. Then according to this principle, each orbital can hold a maximum of 2 electrons, and those 2 electrons have to be opposite spin. One facing up, one facing down. It doesn't matter which is which. The next one is Hund's rule. Then by Hund's rules, when you are filling the orbitals of the same energy level, you have to make sure each orbital has a minimum of 1 electron. Okay, what it is that, for example, that's my P. Okay, and I want to put 5 electrons in this p orbital. Okay, I have 2 choices. Okay, I could go, actually let's go 4, because 5 is not gonna work. Let's go 4. Okay, I want to put 4 electrons in each of these orbitals, p orbitals, and I have 2 choices. One is I go like that. Okay, and the second one I go, sorry about that, 1, 2, 3, and 4. These are my 2 options. Okay, option 1, option 2, or the second option. Then by Hund's rule, what it says is that the orbitals of identical energy level, you want to make sure you have a minimum of 1 electron in each orbital. What that means is that this is the one that will be accepted. That one will be inaccurate. Okay? Then you want to make sure there is 1 electron in each orbital. Okay? Rather than having 2 full orbitals and 1, rather than having 2 full orbitals and 1 empty orbital, what we're gonna have 1 full orbitals and 2 half full. Okay, then if you have 2 electrons, which is the maximum number of electrons you could have in each orbital, we call it a full orbital. If you have 1, we call it half full, and if it's nothing, we call it empty. Okay, this is a full p orbital, like a px. These 2 are half py pz. As I told you guys, I don't know which one is px py pz. I'm just assuming, for example, if this is px py pz. Okay, then this is the Hund's rule. Okay, when we are filling the orbitals of the identical energy level, you want to have a maximum of 1 electron in each orbitals, rather than 2 full ones and 1 empty one. If you do it this way, you will not receive any credit at all. It has to be done like this. Now let's write down the electronic configuration and draw the orbital diagram for hydrogen atom. Then if you look at your periodic table, you will know that hydrogen has 1 electron, right? Hydrogen atom. Okay, then hydrogen atom has 1 electron. Okay, then remember, energy is quantized. We always have to start from energy level 1, then we go to energy level 2, 3, 4, 5, 6, 7. Okay, then in the first energy level, what we have only s orbitals. Okay, then we're going to start from energy level 1. Should be 1. We only have s orbitals. And how many electrons hydrogen has? It only has 1 electrons. That's why it's 1s1. 1 is the principal energy level, and that 1 is the number of electrons. Okay, and S is the subshell that's in energy level 1. Then 1s1 is the electronic configuration for hydrogen atom. Now how do we do the orbitals? Okay, remember we use boxes. This is the box for 1s orbitals, and how many electrons we have in 1s for hydrogen atom? Only 1 electron. Okay, then this will be the orbital diagram. Okay, then the top one is the electronic configuration, and the bottom one is the orbital diagram. Okay, this is the simplest one. Now let's do it for lithium. Again, if you look at your periodic table, you will know that lithium atom has 3 electrons. Okay, then we're gonna start from energy level 1 as always. Okay, then the first one is 1s. What's the maximum number of electrons we could have? It's 2. Okay, and energy level 1, s can have no more than 2. Now lithium has 3 electrons. 2 will be on the energy level 1, But we still need one more, right, to make it to 3. Then we have to go to the second energy level. The second energy level is 2 S. Remember, we start with S. And how many more do we need to make it to 3? One more. Okay. Then if you look here, let me choose a different color. That 2 and this one, then it's 2 plus 1, which is equal to 3. Okay. Now, as you could see, this is the electronic configuration for lithium that has 3 electrons. Okay. Now we're going to do the orbital diagram. For 1s1, we use a box. We always have to say what that box belongs to. 1s, how many electrons does it have? 2. Remember, by Pauli's exclusion principle, the electrons have to be opposite spin. Don't forget that. Okay. Now for energy level 2, 2s1. Okay, again 2s. How many electron is that in this one? It's only 1. Remember, it's 2. We have 2s. Oops. 2s 1. Okay. Then 1s2. That's 1s. You have 2 electrons. Now for 2s1, 2 means we are in energy level 2. We start with the s orbitals because it has a lower subshell. And how many more electrons does we need? Is 1 more, because we have to have a total of 3 electrons. 2 was in energy level 2 and 1 more for energy level 1 more to make it to 3. And how many electrons is there in 2s1 for lithium? It's only 1 electron. You shouldn't put 2, because if you put 2, you will end up with 4, which will not be for lithium. Okay, you only have to put 1. Okay, then this will be the orbital diagram for lithium. For lithium atom. Okay. All right, the top one is the electronic configuration and the bottom one is the orbital diagram. Now let's do it for oxygen. Okay, oxygen has 8 electrons. Then let's do it. It's going to be 1s2, 2s2. Now we have so far 4, 2p. Now it's 4. We need 4 more to make it to 8, right? 2p4. Now we are filling in p orbitals because we're done with s. Then in energy level 2 or principal energy level 2, that's when the p orbitals gonna appear. Okay, and we could have a maximum of 6 electrons in any p orbital. Okay, but we only are using 4 of it. Now if you add the electron, just to double check, you always have to double check to make sure you did it right. That's 2, 2 is 4, and 4 plus 4 is 8. Then this is correct because oxygen atom has 8 electrons. Okay, now, and these ones, one more time, the 1, the 2, and that 2 is the principal energy level. It has nothing to do with the number of electrons. Okay, we had to go from energy level 1 to energy level 2 because we are dealing with 8 electrons. We need to have put 8 electrons. Okay, then in energy level 2, s orbital or s subshell is in lower energy level than p. That's why we're filling the s first, 2s first, and then 2p second. Okay, and that's how it's being done. Now let's do the orbitals. Okay, again 1s2 because it has 2 electrons, 2s2 because it has 2 electrons, and 2p4. Okay, remember p is 3 boxes joined together. Now here we have to follow the Hans rule. What did it say? Orbitals of the same energy level, you want to make sure you have at least 1 electron in each orbitals. Rather than have 2 full, 1 empty, we're going to make sure you have at least 1 in each orbital. That's why we go 1, 2, 3, and 4. Oops. Okay. Right? Okay. This would be the orbital diagram for oxygen atom. Now, what we're gonna do, we're gonna continue writing it for example for fluorine. Okay, let's do for fluorine, which has 9 electrons. Then it's gonna be 1s2, 2s2, 2p, 5. Remember, 2. Now 2 plus 2, which is 4, plus 5 is 9. Okay, now fluorine has 9 electrons. This is done. This will be the electronic configuration for fluorine atom. Now let's draw the orbital diagram. Okay, 1s2, 2s2, now 2p5. Okay, 2p. Okay, then it's going to be 1, 2, 3, 4, 5. Okay, and this will be the orbital diagram for fluorine. To put the electron, as you had noticed, sometimes I go like that, sometimes I go like that. It doesn't matter. Okay, it doesn't matter if it has two little tailed arrow, okay, or it has only one of these. Then let me go use this one. Then as you could see, I'll go with 2 like this or only 1. It doesn't matter. As long as it either has 1 or 2, it's fine. Okay, and as you could see, here I go with 1, but here I've done 2. It doesn't matter. There is no right and wrong. As long as you will show that they have opposite spin, it's all good. Okay, now let's do it for one other atom. Let's do it for neon. Neon is 10. Okay, we go 1s2, 2s2, and 2p6, right? Then if you look and if you add up the electrons, it's 2 plus 2 is 4, 4 plus 6 is 10, and neon has 10 electrons. Then this would be its electronic configuration. Now let's do the orbital diagram. 2, that's 1s2. This one is 2s2. And for 2p. Okay, this is 6. 1, 2, 3, 4, 5, 6. Now, look here. If you look at both the electronic configuration and orbital diagram for neon, you will see neon has a complete full shell. Unlike fluorine. Look at the fluorine. Fluorine still needs one more to have a complete full shell. But look at neon. It's completely full. Where on the periodic table neon belongs to? Okay, it's inert gases. Remember I said group 8, inert gases. Okay, they do not participate in any chemical reaction. Why? Because they have a full electronic shell. They don't need to add or lose electron anymore. Okay, then all the other elements on the periodic table, with the exception of group 8, they're gonna add or lose electron to have a full shell, right? Whereas neon or all the other group 8 elements, they already have a full shell. That's why they do not participate in any chemical reaction. That's why we call them inert gases. Okay, that was the reason for it. Now let's do one more. Okay. Let's do magnesium. Okay. If you look at the periodic table, magnesium atom has 12 electrons. Then it's going to be 1s2, 2s2, 2p6. Now it's 10. Okay? Now we have to go to the next energy level. Why? Because in the second energy level or principal energy level, we only have s and p orbitals. Okay? Now we have to go to the third energy level. And in third energy level, s orbitals has the lowest energy. Okay? That's why we go to 3s. Now, how many more electrons do we need to make it to 12? Then we have so far 10. 2 more, we make it 12. Then C, it's 2 plus 2 is 4. 4 plus 6 is 10. And 10 plus 2 is 12. This is the electronic configuration for magnesium atom. Then I had to go to the next energy level. Then you see, energy levels quantized. You cannot just jump to energy level from energy level 1 to energy level 3. You have to go through energy level 1, then energy level 2, then go to energy level 3. Okay, that's it. And it will be the exact same format when we are removing electron, which I'm going to discuss later. Now let's do the orbital diagram. Okay, 1s2, 2s2, 2p6, and 3s2. Okay, this is the orbital diagram for magnesium atom. Okay, now let's do it for sulfur, which is 16. Sulfur atom has 16 electrons. Okay, then it's 1s2, 2s2, 2p6, 3s2, 3p. Now let's count it how many more we have to add. 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. Now 12, how many more do we need to make it to 16? Need 4 more. Okay, we need 4 more. Okay, now let's add 4 more. 10, 4. Okay, then as you can see, let's double check. 2 and 2 is 4. 4 and 6 is 10. 10 and 2 is 12. 12 and 4 is 16. Okay, this is the electronic configuration for sulfur. And I double check and I made sure that I have 16 electrons. Then these superscripts are the number of electrons. These 1, 2, and 3s are the principal energy level or energy level. Okay, now let's draw the orbital diagram. Okay, that's 1s, 2s, 3p, 1, 2, 3, sorry, 2p, 2p6, 3s2, and 3p4. Okay, and it's 1, 2, 3, 4. Okay, now this will be the orbital diagram for sulfur atom. Okay, and that's electronic configuration. Then my recommendation too is that always count the number of electrons. Make sure you don't make a mistake, because if you make a mistake on the number of electrons, then will not be the atom that we will be working with anymore. Okay, now let's do one more. Let's do argon. Okay, argon has 18 electrons. Let's change colors just for fun. Okay, argon, 18 electrons. Let's write the electronic configuration. It's 1s2, 2s2, 2p6, 3s2, and 3p6. Now if we count here, Give me 1 sec. All right, it's 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 6 is 18. Okay, this will be the electronic configuration for argon. Now draw the orbital diagram. 1s2, 2s2. We do the boxes. 2p6. 3s2, 3p6. Okay. Let me fix that so that it looks nicer. This will be the orbital diagram for argon. And as you could see, argon has a full electronic and orbital shells. Okay, that's why if you look at the periodic table, argon is in group 8. Okay, argon is in group 8. That's why it has a full shell, and that's why it does not participate in any chemical reaction. Because once atoms have full shell, that means they have reached their lowest energy level. That's where they are the happiest the most. That's why they do not participate in any chemical reactions. Okay. Now, let's do calcium. Okay, calcium 20. Okay, there's 1s2, 2s2, 2p6, 3s2, 3p6, okay. Now, if you look here, in energy level 3, that's where the d orbitals start appearing, right? In energy level 3. But if I was going to do that, I would say it's 3d2, right? Okay, if it would have been correct, if it would have followed the order, like first we do all the S's and the P's and the D's and etc. But the reality is that, remember that I said the these subshells, which are S, P, D, and F orbitals, they also have their own energy levels. And saying that 4s orbital is at a lower energy level than 3d orbital. Okay, then 4s orbital, let me change the color. 4s orbital or subshell is at a lower energy level than 3D subshell. Okay, therefore we write 4s first, then 3D. Okay, then what happens is that instead of writing 3D2, what we will write, this will be wrong. Actually, let me write it again. Then what we will write, we write it as 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. That's what we write. Okay, and this one is incorrect, whereas this one is correct. Okay, Then if you write it this way, that's incorrect. You will not receive any credit at all. Why? Because 4s orbitals or subshells are at a lower energy level than 3d subshells. Okay? That's why you have to write 4s first. Okay? That's how it works. Okay? Now, let's draw the orbitals for it. And it's probably I'm gonna run out of space, I think. Yeah, it wouldn't let me do it. Okay. Let me do it somewhere. I'll put it up here. Okay. Then it's 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Okay. 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 This will be the orbital diagram for calcium. Now, let me go back. Look here. Look at the electronic configuration for magnesium and for sulfur. And look at your periodic table. Okay? Magnesium is a metal, right? And sulfur is a non-metal. Okay? And look at the very last orbital or the subshell that we fill in for magnesium and sulfur. For magnesium, the very last one is 3s2. What about for sulfur? For sulfur, the very last one is 3p4. Okay? Then, what is the conclusion? Is that for metals, the very last subshell that we fill in is always an s orbital. Whereas for non-metals, the very last orbital that we fill in is a p orbital. Okay? It doesn't matter which subshell, which electronic energy level, or what would be the number of electrons. One thing that you want to pay attention is that for metal, such as magnesium, the very last subshell that we fill in is an s orbital. Whereas for non-metal, such as sulfur, the very last subshell or orbital that we fill in is a p orbital. Okay? Then when you wrote your electronic configuration, for example, for sulfur, and for some reason, the very last one was an S, you made a mistake. Okay? The last one has to be a P. Okay? And if I go back and you look at my other examples, okay? Look at hydrogen. Okay? Hydrogen is sometimes a metal, sometimes a non-metal. Here is like a, let's go to the lithium. Lithium is a metal. What is it? The very last orbital is S. Okay? Let's go to oxygen. Oxygen is a non-metal. The last orbital is P. You see? Let's go to fluorine. Let's go to neon. They are both non-metal. The very last orbitals or subshell is a P. I've already talked about magnesium and sulfur. Argon, non-metal. The very last orbital is a P. And look at calcium. It's a metal. The very last orbital is an S. Okay? Then as I said, it doesn't matter how many electrons or what is its principal energy level. One thing that you want to pay attention, or maybe I'm going to write it down here because I have a space for, okay, element, okay, last subshell. chemical orbital. Okay, let's fill in. Then if your element is a metal, the last subshell is a S. Okay, if it's a non-metal, the very last subshell is a P. If it's a transition metal, let's go green. Transition metal. The very last subshell is a D. And let's go light blue. And lanthanides, and actinide series, lanthanide, I write it as LAN and actinide series. The very last subshell, it will be F. Okay, then make a note of that. Then if you know that, you could always double check your electronic configuration and your orbital diagram. Okay, then one more time, if it's the element that we are writing the electronic configuration for, or the orbital diagram, it doesn't matter. If it's a metal, the last subshell is S. If it's a non-metal, last subshell is P. If it's a transition metal, last subshell is D. And if it's a lanthanide and actinide series, okay, they will be F. Okay, that's how you always can double check with yourself to make sure you've done it correctly. All right, then as you could see here, this is the electronic configuration. Actually, it's the last one, the last part, for some of the metals and some of the non-metals. Look here, okay, with the exception of hydrogen. Hydrogen is the exception to the rule. You will see lithium, beryllium, magnesium, and sodium. For them all, the very last subshell that we are filling in are s orbitals. Okay, again, hydrogen and helium are the exception to the rule, although they are non-metals, but we are doing the s orbital. Those two are the exception to the rule. And look at boron, look at carbon, nitrogen, oxygen, fluorine, neon, argon, chlorine, sulfur, phosphorus, silicon, aluminum. Okay, these are all non-metal. You will see the very last subshell that we are filling in, you see, it's the P. Okay, and if you look at group 8, which is our inert gases, you will see they have a completely full subshell, okay, or electronic configuration. That's why they do not participate in any chemical reaction. They have reached their lowest energy level. They're happy where they are. They don't need to participate in any chemical reaction, whereas the rest of the elements, they still need one more or two more and etc. to reach that full electronic configuration. That's why they do participate in chemical reaction. Okay. Now let's go to the next slide. Remember that I told you guys then the principal energy level has its own energy level. Then it's the lowest is at principal energy level 1, then it will be principal energy level 2 and 3 up to 7. And I also said the subshells or orbitals, they have their own energy level. Then look here. Then if you look here, 1s is the lowest energy level that we have. Then it's 2s, 2p, 3s, 3p, and then 4s. This is the example that I talked about for calcium. Remember, I did 4s first rather than 3d. Then it's 4s first, 3d, okay, and 4p, 5s, 4d. Okay. Then if I go to the next slide, this is the order that we filling the orbitals, which you have to memorize. There is no other way of doing it. That has to be memorized, and that's in the order of energy level. Then you see, after 3D, we don't go 5s or 4s. Then we go 4p. Then after 3p is where the 4s is. Okay, then as you could see, starting energy level 3, everything is not following the pattern that it's supposed to, because subshells have their own energy level. And this is something that you need to memorize. There's no other way around it. You have to memorize that. Okay, once you have this memorized, you should not have any problem writing down the energy level. Okay. Now, one other thing. Okay, let me go back to here. Actually here. Okay, look at lithium. It's a metal. The last subshell is white, S, because it's a metal. Okay, what do metals do? Metals lose electron, right? Why do they lose electron? Look at it. 2s is a half-filled orbital. Once it loses electron, what happens? It becomes white. Only 1s, which is a complete shell. Okay? Now, look at my oxygen. Oxygen, non-metal. P orbital is the last orbital, or the subshell. Okay? And look here. If I give 2p one more electron, what would it have? It will have a complete full shell. Okay? That's why what happens is, two more. If I give oxygen 2 more electrons, it will have a complete shell, right? Full shell, right? That's why oxygen is a non-metal, right? That's why non-metals gain electrons. That's the reason that we say metals lose electron, non-metals gain electron. Look at magnesium and sulfur. Okay, magnesium and sulfur. Okay, then sulfur, if you give 2 more electrons to sulfur, okay, it will have a full 3p orbitals. Okay, and that's the reason behind the fact that we say electrons gain metals gain electrons, non-metal lose electrons. Okay, that's the key. Then also, when metals lose electrons, okay, like lithium loses 1 electron. If it loses electron, what happens? It will have the same electronic configuration as helium, right? If lithium loses that 1 electron, okay, it has the same electronic configuration as helium. Look here. Okay, let me go back to lithium. Look at here, lithium. Okay, if it loses that 1 electron, okay, it will become 1s2. Then it becomes 1s2. I don't have the electronic configuration for helium. Okay, then lithium, it loses 1 electron. It will have the same electronic configuration as helium. Okay, whereas fluorine, when it gains 1 electron, it will have the same electronic configuration as neon. Okay, remember when I was going over, I think it was chapter 4, talking about metals and non-metals, they said they either gain or lose electron, so that they have the same electronic configuration as the inner gases. That's what it is. Okay, that's why lithium loses 1 electron, because that's the only way it could have the same electronic configuration as helium. Okay, or beryllium loses 2, it will have the same electronic configuration as helium. Or magnesium loses 2, it will have the same electronic configuration as neon. Or chlorine gains 1 electron, and by doing so, it will have the same electronic configuration as argon. Okay, that's the reason behind why some elements or some metals some metals lose 1 or 2 electrons, or while some non-metals gain 2 or 1 or 3 electrons. Okay, just to have the same electronic configuration as the non-metal. Right. Then let's go back and talk about the periodic table one more time. Then if you pay attention here and everything that I went over, then for the metals, okay, with the exception of hydrogen and helium are the exception to the rule. They are the only non-metal that the last orbital or subshell is the S. But the rest, okay, the very last subshell that they are filling in is the S. For non-metal, it's P, including inert gases. Then for transition metals, as you can see here, it's the D block, is the last subshell. And for lanthanide and actinide series, as you can see here, is the F subshell. Is the very last subshell that they are filling in. Okay, then make a note of that, have that somewhere, so that when you are writing the electronic configuration, that's another way of checking it if you done it correctly or not. Always look at this last subshell and look at what type of an element you're dealing with. If it's a metal, S is the last one, non-metal is P, transition metal is D, and lanthanide and actinide series will be F. Then chemistry is not a chemistry without exceptions. Then these are, you see these dots do not follow the same pattern for when we are writing the electronic configuration. Okay, then if they they do not follow the same pattern, then these are the exception to the rule. Okay, then you have, and it's only these transition metals, okay, which you need to know that these are the exception to the rule. And what do I mean that they are the exception to the rule? Then what we're gonna do, I'm gonna write down the electronic configuration for vanadium. Let's write down the electronic configuration for vanadium, and I will tell you what I mean by that they are the exception to the rule. Okay, then excuse me, then vanadium has 23 electrons. Okay, let's write it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, sorry about that, 4s2, and 3d. Now how many more do I need to add? I need to add 3 more. Okay, then let's add it up. Okay, it's 2 plus 2 is 4, plus 6 is 10, 12, 18, 20, 23. Okay, this is the electronic configuration for vanadium. Now let's do the diagram for it. Orbitals. Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d3. Okay, there's 3d3. Sorry, I need to do one more. Okay, the orbital is 5. Then we're gonna follow Hund's rule. Okay, then it has to be 3. Then we're not gonna put 2 here, 1 here. Remember, orbitals of the same energy level, you want to have a maximum of 1 electron in each orbital. Okay, then we go 1, 2, 3. Okay, and we're going to double check. Vanadium, where is it? It's a transition metal. Then what's the last orbital that we have to fill in? The orbital. Have we did it? Yes, you did it correctly. Now, what I'm going to do next, I'm going to write the electronic configuration for chromium. Because as you could see here, after vanadium is chromium. Okay? And chromium is the exception. And why it is the exception? Let me write it down in different color. Okay. And chromium has 24 electrons. And it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. That makes up to 24 electrons. Now let's do the orbitals. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. Okay, 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4. I'm following the Hans rule. Okay. Now, if you look here, what it is here, chromium, if it would have one more electron, okay, it would have had a half full 3D subshell. Okay, then what's the exception about? The exception says, let me write it down here. Based on the exception, half full, d orbitals, half full or completely full d orbitals are favored. Okay, let me write it down properly. Are favored. What does it mean by favored? It means they are more stable. Okay, if we could have our element or our transition metal to have a half full d orbital, that's what we're gonna do. Then if I go back to here, you could make that 3 orbital to be half full by moving one of the electrons from 4s to 3d. Then what happens is that 4s is at a lower energy level than 3d. What happens is that rises, and these two will have the same energy level, and one of the electrons from 4s goes to 3d. Okay, and I'm going to write it here. Let's go with blue. Then actually for chromium, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Now let's do the orbital diagram. Okay. 1, sorry about that. 1s, 2s, 2p, 3s, sorry, I made a mistake here. Should be a P, not a D. 3P. Now we have 4s1, and we have 3d5. Okay, 1, 2, 3, 4. Then as you can see here, that 3D is half full subshell. If it would have followed the pattern, this would have been. But since for d orbital only, it's only d orbitals, half full d orbitals are most stable. That's why what happens is that one of the electrons from S moves to the D, and this will become its electronic configuration. Then this is wrong. Okay, I'm gonna put a line, okay, and this is wrong. I'm gonna go over it in red. That is a good color. Okay, and this will be incorrect. If you do that one, you will not receive any credit. This, the one in blue, is the correct electronic configuration on orbital diagram for chromium. Okay, then if I go back, that's why chromium is the exception. If I even go back one more slide, oh, let me go back one more. Okay, now let's go back to the exception. You will see here that chromium was the exception to the rule. You will see its electronic configuration is not following the format. There are more with the exceptions to the rule. Okay, molybdenum also exception to the rule. This 41 is the exception to the rule. Okay, then these are all the exception to the rule. You see, we have 5s1. Okay, and silver is the exception to the rule. Gold is the exception to the rule. And just know those elements that they are the exception to the rule. Okay, then the electronic configuration is slightly different, because for d orbitals, half full d orbitals are favored. Okay, that's why one of the electrons from the s orbitals, the one right before that, moves and makes that d orbital a half full shell. Okay, then that's the reason for it. Now, how do we write the noble gas core notation or shorthand? Okay, sometimes rather than writing the whole electronic configuration, we're going to use a noble gas shorthand. And to do so, we always look at the noble gas or inert gas that's before the element. Okay, let me go back. Then for sodium, what is the noble gas or inert gas before it? It's neon. For chlorine is also neon. For bromine is argon. Okay, we always look at the noble gas or inert gas that's coming before. Now, remember I told you guys that group 8, they have a full shell. Okay, then if you look here, helium is in row 1, right? You see that 1s2 is the last one. What about neon? You see that? Row 2. There's 2s2, 2p6. Argon is in electronic principal energy level 3. Okay? 3s2, 3p6. Krypton is 4s2, 4p6. Xenon is 5s2, 5p6. And radon is 6s2 and 6s2, 6p6. You have to memorize, okay? Then when you are using the shorthand noble gas radiation, you always look at the noble gas that comes before that element. If it's a metal, non-metal, transition metal, it doesn't matter, okay? Now if I go back to my example, look at sodium, okay? Then up to here, remember, 2s2, 2p6, 2s2, 2p6, which one is it? It's neon, okay? Then up to here, let me change my color. Then up to here, that will be the electronic configuration for neon, which I write it. And the rest will be for sodium. Then that way, this way, is how we write the noble gas core notation for sodium. Okay, that's how it's written. Then rather than sitting down and writing all those S and P and D's, you could use the noble gas that comes in front the first before that element and write the rest, which will be for the element itself. And you always have to make sure that your noble gas will be in bracket. It has to be in always bracket. Okay. Now let's talk about classifying electrons. I've talked about this in the past, but let's talk about it in more detail. Okay. Then we have core electrons and we have valence electrons. Core electrons are the inner electrons, okay? Whereas valence electrons, by definition, they are those electrons that are at the highest principal energy level, okay? That's the valence electron, okay? They are at the outermost or highest principal energy level, okay? Now, what do I mean by it? Okay. This is the electronic configuration for neon. Okay. Let me change it. Okay. This will be the electronic configuration for neon. Okay. Now, why neon has 8 valence electrons? By definition, valence electrons are those electrons at the highest principal energy level. Now we have two energy level here. We have two energy level 1 and we have energy level 2. Which one of these are highest? Okay, that's energy level 2. Energy level 2 is the highest. Then those subshells that are in energy level 2 will be your will be your outmost subshells. Okay. Then S and P and those electrons that are on those S and P subshells will be your valence electron. Okay. Then 6 and 2 is 8. Okay. Why? Because 2, that 2 belongs to 2s, that 6 belongs to 2p. Then between energy level or principal energy level 1 and principal energy level 2, then principal energy level 2 is at a higher energy level. Okay, and those orbitals that are in that energy level will be your valence shells. Okay, then 2s and 2p is your valence shell. And how many electrons total there is? It's 6 and 2 is 8. That's why neon has 8 valence electrons and the rest will be core. Okay. Then neon has how many electrons? Neon has 10 electrons. Okay. Neon has 10 electrons. Okay. Right? Neon has 10 electrons. Then now that you know its valence electron is 8, how about core electron? It will be 10 minus 8, should be 2. The neon has 8 valence electron and 2 core electron. Okay, That's how you will calculate valence and core electrons for any element. Also, elements with the same valence electrons, they usually show the same or similar chemical characteristics and behavior. Now let's look at silicon. This is the electronic configuration for silicon. Now, where is silicon's valence shell? Remember, valence shell are those at the highest principal energy level. Between 1, 2, and 3, 3 is the highest. And how many electrons there is? It's 2 coming from S and 2 coming from P. Therefore, silicon has 4 valence electron, okay, and how many core electron is 4. Silicon in total it has 14 electron, right? 14 minus 4, it's 10. Okay, that's the total number of core electron that silicon has. Now, let's do it one more for selenium. Okay, selenium has 34 electrons. This is the electronic configuration for selenium. Okay, now look here. How many subshells we are filling in? We are filling in principal energy level 1, principal energy level 2, principal energy level 3, and 4. Okay? Then between 1, 2, and 3, and 4, 4 is the highest energy level. Okay? Now, in that 4, how many subshells that we have? 4s2 and 4p4. Okay? That's why these are your valence shell. Okay? These are your valence shell. That's why selenium has 6 valence electron. Okay, it's 2 plus 4, which is 6, and it has 28 core electrons. Why? Because 34 minus 6 is 28. Okay, that's how we figure out core and valence electron. You always go and look at the highest principal energy level, and you will see how many subshells is in that and how many electrons those subshells are carrying. That will be your valence electrons. And when you subtract the valence electrons from the total number of electrons, you will know it's the core electron. Okay. Then we could always add or remove valence electrons, but we cannot touch the core electrons. Okay. Then every time we are adding or removing the electron, we are adding, removing from the valence electrons. And we can never touch the core electrons, okay? Because they are the closest to the nucleus, and it's very, it's not thermodynamically feasible to remove electrons that are closest to the shell. Remember, negative, positive, they attract. It requires a lot of energy to do that. All right. Now let's do these problems. Let's go to pen. Okay, what we're gonna do, we're gonna write down the complete electronic configuration and shorthand electronic configuration or noble gas core notation. We're gonna draw the orbitals, and we're gonna indicate how many valence, core, and unpaired electrons we have. Okay, then let's do it. Let's do it for calcium. Then if you look at the periodic table, calcium has 20 electrons. There's going to be 1s2, 2s2, 2p6, 3s2, and 4. Sorry, where did I mess it up? 3p6 and 4s2. You always double check that you have the exact number of electrons, which is 20, and I have 20. Then this will be the complete electronic configuration for calcium. Now let's draw the orbital diagram for it. Okay, that's 1s2, 2s2, 2p6, 3s2, and 3p6, and 4s2. Okay, this will be the orbital diagram for calcium. Now we're going to do the shorthand. Okay, then look at the noble gas that comes before calcium. It's argon. Okay, let me go back to a periodic table. Then the noble gas that's coming before calcium is argon. Argon is in period 3. Then it will be the last orbital. It's going to be 3s2, 3p6. Okay, that's why. Okay, then all the way to here is for argon. Okay, even if you don't want to memorize that, you will know argon has 18 and count it. 2 and 2, 4, 4 and 6, 10, 12, 18. Then this is for argon. Okay, and the rest will be for calcium. Okay, that's how we do the shorthand. All right, now we want to indicate how many valence electron, core electron, and unpaired electron this atom has. Now for valence electron, you have to look at the highest principal energy level. You have energy level 1, 2, 3, and 4. Which one is the highest? It's principal energy level 4 is the highest. How many electrons there is in principal energy level? 2. Okay, that's why calcium has 2 valence electrons. How many core electrons? 20 minus 2, which is 18. How many unpaired electrons? For unpaired electron, look at your orbitals. Do you see any orbital with unpaired electrons? No, everything is paired up. That's why it does not have any unpaired electrons. It's 0. Okay, that's how we answer these type of questions. Let's do one more. Let's do it for bromine. Okay, bromine has 35 electrons. Okay, now let's write down the electronic configuration for it. Okay, this is the electronic configuration for bromine. If you add it up, you will know it will be 35 electrons. Okay, now we're gonna draw the orbital diagram. Okay, then I need more space. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. Again, follow Hund's rule. 1, 2, 3, 4, and 5. Okay, this will be the orbital diagram for bromine, right? Now let's do the shorthand. Look at the periodic table, okay? The inert gas that comes before bromine is argon, okay? Argon is in row 1, 2, 3. Then the last orbital that's filling is 3s2, 3p6. Okay, 3s2, 3p6. Then this is the last one. Then up to here is for argon. And the rest will be for bromine. Or P5. Okay. Now what we're gonna do next, we are going to indicate how many valence electron, core electron, and unpaired electron this element has. Then for valence electron, we have to look at the highest principal energy level. Then we have 1, we have 2, we have 3, we have 4. Okay? Then this is 4, and that's 4. Okay? What are the subshells? Is S and P. Then how many electrons? Then 2 is coming from 4s, and 5 is coming from 4p. Okay? Let's write it down. Okay, then this is the subshell. Let me highlight it. Maybe it's a good idea to highlight it. Highlight it in one. I'm not going to cover it. And these are, maybe not a good idea. Let me use the pen and use this. This one and this one is our valence shell. Okay, and how many electrons in valence shell? It's 2 plus 5, which is 7. Okay, then bromine has 7 valence electrons. Okay, now how many core electrons does it have? It's the total number of electrons minus valence, which is 35 minus 7, which is 28. Okay, then bromine has 7 valence electrons and 28 core electrons. Now, how many unpaired electron? For the unpaired electron, we look at the orbitals. Look here. Everything is paired up except here. How many unpaired electron does it have? It only has 1 unpaired electron. Okay, that's how we do it. Also, let's talk about one more thing. Okay, look here. Remember I said all the elements in the periodic table are going to gain or lose electron to have like the same electronic characteristics as in inert gases, group 8. And they always want to have the same electronic characteristic as the noble gas before them. Then sodium, this is its last electronic configuration. Then if it loses 1 electron, it will have the same electronic characteristics as neon. That's why we say sodium is +1. Look at magnesium. How many electrons does magnesium have to lose to have the same electronic characteristics as neon? It has to lose 2. Okay. Now, remember, also metals lose electrons. Now look at the nonmetals. Nonmetals want to have the same characteristics as the halogen that comes in front of them. Look at sulfur. How many more does it have to gain to have the same electronic characteristic as argon? 2. Look at the chlorine. 1 more. That's why the charge on all the elements or nonmetal in group 6 is -2. In group 7 is -1. It's just you have to look and see how many electrons do they want to lose to have or gain to have the characteristics as the noble gas. For metals, it's going to be the noble gas that's coming before them, and for nonmetals, it's going to be the noble gas that comes after them. Okay, look at phosphorus. Phosphorus has to have 3 more to have the same characteristics as argon. The same thing with nitrogen, has to have 3 more. Oxygen and all the nonmetals in that group has to gain 2 more. Fluorine and all the nonmetals in group 7 has to gain 1 more. That's why the charge in group 7 is -1, group 6 is -2, group 5 is -3. Or for group 1 is +1, group 2 is +2. This is the reason behind it. Okay, now let's continue with our example. What we're gonna do, we're gonna write the complete electronic configuration for zirconium. If somebody asks you to write the electronic configuration, it does not tell you write the complete or the shorthand notation. It's your choice. You could choose whichever. But once you're told to write the complete electronic configuration, that means you have to write the long one. Okay? The zirconium, if you look at the periodic table, has 40 electrons. Okay? Then it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 4p6, 5s2, and 4d 2. Okay, let me count. 6 and 2 and 2, 10, 12, 18, 20, 30, 36, 37, 38, 39, 40. That's 40. You always have to count. That's why sometimes I go slow, because I'm just counting to make sure I'm doing it correctly. You need to count. Okay? Then this is the complete electronic configuration for zirconium. Now look where on the periodic table it is. It's a transition metal. Then look what is the last element, last subshell I'm filling in. It's a D. Okay, that D subshell is the last one that I'm filling, and that's an indication that you did it correctly. Now we're gonna do the orbital diagram. Since it's gonna take a long time, I'm gonna do the very last one. Okay, you have to do all of it, but since for just today and for the purpose of teaching, since it's gonna take a long time for me to do it, I am gonna skip to the very last one. Okay, but on the exam you cannot skip it. Okay, let's do 5s2 and 4d2. Okay. Then you have to do, as I said, all of it. Now, we're going to do the shorthand. For zirconium, the very last, the noble gas before zirconium, what is that? It is krypton. Okay, krypton is in row 4, then 4s2, 4p6, 4s2, 4p6, then up to here will be for krypton, and the rest will be for zirconium. It's going to be krypton, 5s2, 4d2. Then this is the noble gas core notation. Now, how many valence electron? Core electron and unpaired electron this element has. Then for the valence electron, you're gonna look at the highest principal energy level. We have 1, 2, 3, 4, 3, 4, 5, 4. Which one is the highest? 5 is the highest, as you could see here. Then 5 is our valence shell. Okay, then 5 is our valence shell. How many electrons there is on that valence shell? It's 2 electrons. That's why zirconium its valence electron is 2. How many core? 40 minus 2, which is 38. Now, how many unpaired electron does it have? Then these are all full, okay? I didn't write it, but they were all full. Then the unpaired one, it only is at subshell 4D, which has 2 unpaired. Do not look at the empty one. For the empty one, we don't care, okay? We only are asking for unpaired electron, okay? Then it's 2. Then zirconium has 2 unpaired electron. Okay. Also, zirconium, it's not one of the exceptions, because if you add 1 electron from 5s, it's not going to make it a half shell d orbital, okay? Still, you need to add 2 more. That's why zirconium is not one of the exceptions. It's right. Now let's do cadmium. Cadmium has 48 electrons. So 4p6, 5s2, and 4d10. Okay, that makes it, if you add it all up, it adds up to 48. Let me double check. That's 16. 2, 2, 6 is 10, 12, 16, 6 to 10, 12, 18, 20, 30, 36, 37, 38, 48. Okay? Right. This will be the complete electronic configuration for cadmium. Now we're going to do the orbital diagram. I'm going to do it for the last 2, just for the purpose of teaching. Again, on the exam, you have to do it for all of it. And while you are taking the notes, just take your time and write it for them all. Okay, now 10. 2, 4, 6, 8, 10. Okay. Now for the noble gas core notation, we always going to look at the noble gas that's come before cadmium. Before cadmium is krypton. Krypton is in row 4. Then up to here is for krypton, and the rest will be for cadmium. Okay, now let's write down the valence electron, core electron, and unpaired electron. For valence electron, you want to look at the highest valence shell. Then we have 1, we have 2, we have 3, we have 4, 3, 4, 5, and 4. Then which one is the highest? It's the 5. You see here, 5. Okay, now let's change color. That is our valence shell. How many electrons is it on valence shell? 2, which is our valence electron. Now for core, it's 48 minus 2, which is 46. Now for unpaired electron, look here. Do you see, well, everything before that I didn't write it, but these are also full. Do you see any unpaired electron? No, everything is filled up. Okay, now that makes that to have 0 unpaired electrons. Okay, let's do one more. Now we're gonna write it for iodine. If you look at the periodic table, iodine has 53 electrons. Let's go down. Has 53 electrons. 53. Okay, then it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and 5p5. Okay, this will be the electronic complete electronic configuration for iodine. Okay. Now for the orbital diagram, I'm only going to do the last two. Okay, again, one more time, on the exam you have to do all of it. 4d10 and 5p5. 1, 2, 3, 4, 5. Okay, now for the shorthand, you want to look at the noble gas that's come before iodine, and before iodine is krypton. Okay, krypton is in row 4. That's why up to here is for krypton, and the rest will be for iodine. As I said, you could always count it, okay? But it takes more time. Right, this is the shorthand noble gas core notation for iodine. Now, how many valence electron, core electron, and unpaired electron does it have? Now, for valence electron, you're gonna look at the highest principal energy level. Then we have 1, 2, 2, 3, 3, 4, 3, 4, 5, 4, 5. Then 5 is the highest, okay, as you can see. Okay, this one and this one. Okay, now how many electron is that? Then it's 2 and 5, which is 7. Okay, then iodine has 7 valence electron. Now, how many core electron does it have? It will be 53 minus 7, which is 46. It has 46 core electron. Now, for valence electron, for unpaired electron, how many unpaired electron does it have? Then everything before 40 is all paired up. The only unpaired is one here. Okay. Then iodine has only one unpaired electron. Okay, let me this is not written nicely. Okay. Okay. Then iodine has only one unpaired electron. Then if you are ever gonna get a question, this is a typical question that I will usually ask. I will give you an element, could be from anywhere on the periodic table, and I ask you to write a complete electronic configuration, the shorthand gas notation, the valence, core, and unpaired electrons, and then draw the orbital diagram. Then these are the typical questions that I ask. Just to make sure that whenever you are writing then the orbital diagram, drawing the orbital diagram, you always have to tell me which that orbital belongs to. Even though it's up there, but you still have to write it down. And always make sure you have the exact number of electrons, because if that number of electrons is not the same as what you want, you're not answering the question, and you will not receive any credit at all. Okay, now let's talk about the atomic properties and the periodic table. Then the first thing that I'm going to first talk about is the ionization energy. By definition, is the amount of energy required to remove an electron from an atom or ion. That's what by ionization means. We're going to remove an electron. Okay. Now, for magnesium is in group 2. Okay, then when we remove the first electron, that's the ionization energy. When we remove the second electron, as you could see, the ionization energy is getting bigger. Okay, and for third one, it's really high. Why? Let me write down the electronic configuration for magnesium. The magnesium is 12. Okay, then when we remove, okay, let me also write down the valence electron. Valence electron, it has 2. Core electron, it's 10. Okay, 12 minus 2, it's 10. Now, when I remove the first electron, we always start from valence shell. Okay, then I am removing it from the valence shell. That's why we don't need a lot of energy. You see, the first energy is low. Now, when I'm removing the second electron, what it is that I'm getting slightly closer to the core. Okay, that's why it's high. It's a slightly higher than the first ionization energy. But look at the third ionization energy. It's like about 6 times higher than the second ionization energy. Why? Because now we are removing from the core electron. Okay, that's why the third ionization energy is higher, because core electrons are tightly bound to each other because they are the closest to the nucleus. That's why for magnesium, the first 2 ionization energy is not as much, but the third one is very high because we are removing from the core electron. Then from 1s2 to s2 2p6 is our core shell. Let me write it down. This is the core, and this one is the valence. That's why it doesn't need too much energy to remove the valence electron, but we need a lot of energy to remove the core electron. Now what I'm going to do here, I'm going to write down the electronic configuration for the ion. Then how do we write the electronic configuration for the ions? Okay, now let's write down the electronic configuration for calcium ion. Then remember what I told you guys. Remember that we can always add or remove electron from the valence electrons. We can never touch the core electrons. Okay, as explained in when I was talking about ionization energy. If you remember, for magnesium, the first 2 ionization energy was low, but the last one was very high because I was trying to remove the electron from the core electron. Okay, now to write down the ionization energy for ions, the first thing that you want to do is to write down the electronic configuration for the ion. The first thing that you want to do is to write down the electronic configuration for the atom itself. Okay, then for calcium ion, don't write it for calcium ion. The first thing that we want to do it, write it down for the atom itself. Okay, then calcium has 20 electrons. Okay, this is the electronic configuration for calcium, which has 20 electrons. Okay, now what you want to do next, go and look for the core for the valence shell. Then what we have 1 2 2 3 3 4. The valence shell is the one with the highest principal energy level, which is 4. Okay, then 4s is our valence shell. Okay, valence shell. Okay, then we're gonna remove electron from the valence shell. Okay, now once you know which one's your valence shell, what you want to do next is to write down the electronic configuration now for calcium ion. Okay, it's going to be 1s2 2s2 2p6 3s2 and 3p6. Okay, right, because calcium has, as you could see, calcium ion is 2 plus. That means we are removing 2 electrons from the valence shell. That's why that's where it's gonna go away. Okay, this is the electronic configuration for calcium ion. One other thing that you could do, you could write for S0, or you don't have to write it. One thing that I recommend not to do, you don't want to say, okay, calcium atom has 2 electrons. Now for the ions, it's 20 electrons. For calcium ion is less 2 will be 18, write it for 18. Okay, it works when we are writing it for metal and non-metals, but when you write it for transition metal, it's not gonna work. It's gonna fail. That's why I really want you guys the right way to do it is write the electronic configuration for the atom itself, then look for the valence shell, and then you will look what is the charge on that ion, and then you're gonna remove based on the charge, either add or remove electron to that valence shell. That's how we do it. Now let's do it for oxygen. Then again, do it for oxygen atom. Oxygen, it has 8 electrons. Okay. Now, second, you're going to look for the valence shell. This is the valence shell. Then oxygen ion, we're going to add 2 electrons. Okay, where are we going to add it? We cannot add it to 2s because it's already full. Where can we add it? We're going to add it to 2p. Okay, and for oxygen ion, okay, this is the electronic configuration for oxygen ion. Okay, as you could see, now it has a full shell. It has the same characteristics as neon. Whereas if I go back to calcium, now calcium ion has a full shell and it has the same characteristic as argon. Okay. All right. Now let's do it for cadmium. Then to write it for cadmium ion, first we're gonna write it for cadmium itself, which has 48 electrons. Okay. This is the electronic configuration for cadmium atom itself. Once you write the electronic configuration, look for the valence shell. Okay, valence shell is the one with the highest principal energy level. Okay, this is your valence shell. Okay, now for cadmium ion, we are gonna remove only 1 electron, and you're gonna remove it from the valence shell. Okay, now I'm gonna remove only 1. Okay, then look here. This is my valence shell, and I'm removing 1 electron for cadmium ion. Then, as I told you guys, if you go and say, okay, cadmium ion, I have to add less, I have to deduct 1 electron, is plus 1, and write it for 47, it will not be correct because you are removing electron from the core shell, which is not right because it requires a large amount of energy. We always add or remove electrons that are on the valence shell or valence electron. Okay, that's why it is better to write the electronic configuration for the atom itself and then do it for ions. If you write it for major group metal and non-metal, it works, but for transition metals and lanthanide actinide series, it will not work. You have to do it from the valence. Find your valence shell and add or remove electron. Actually, it's a metal. You're gonna remove electrons from the valence shell, as I did in this particular example. Now, let's talk about the atomic properties and the periodic table. Okay? Then, by definition, ionization energy is the amount of energy required to remove an electron from an atom. Okay? That's the ionization energy. Okay? Then what we're going to do, we're going to remove an electron from an atom. Okay? Then, what it is that ionization energy, you want to remove an electron. What species or what element on the periodic table they want to get rid of the electrons? It's the metal. Okay? But for non-metals, they want to hold on to the electrons. Okay? That's why the ionization energy increases as we go to the right. Okay? Why? Because non-metals want to hold on to their electrons. By definition, ionization energy is the amount of energy to remove an electron from an atom. Okay? Non-metals, they want to get rid of the electrons. Sorry, metals want to get rid of the electrons. Non-metals want to hold on to their electrons. Okay? Let's write this down. Non-metal want to hold on to electron. Metal get rid of or just write lose electron. Want to lose the electron. Okay, and ionization energy is the amount of energy to remove an electron. That's why as we go toward the non-metal, ionization energy increases, because you're going to have a harder and harder time to remove the electron, because non-metallic characteristics increases. Remember the fluorine has the highest electronegativity. Remember, is the highest non-metal, and francium is the most or highest metal. Okay, always remember that. Okay, that's why as we go from left toward the right, non-metallic characteristics increases. That's why ionization energy increases, because you need more energy to remove the electron, because non-metals want to hold on to their electrons. Whereas as we go down the group, ionization energy decreases. Why? Because metallic characteristics increases. Metals want to get rid of their electrons. That's why you don't need too much energy to remove the electron. Okay, that's the reason. The ionization energy increases as we go from left to right, and it decreases as we go from top to bottom. Okay, always look at the location of non-metal. As we move toward the non-metal, you need more energy to remove the electrons, because non-metal want to hold on to the electrons. And as we go down the group, the metallic characteristics increases. That's why it's easier to remove the electron. That's why ionization energy decreases. You don't need too much energy to remove the electrons, since metal want to get rid of their electron anyway. Okay. Now, metallic characteristics and non-metallic characteristics is just the same. Okay, then as we go to the left side of the periodic table, from left to right side, from left to right, we have more non-metal. Then if we have more non-metal, the metallic characteristics decreases. And as we go from top to bottom, the metallic characteristics increases, because francium has the highest metallic characteristic. Okay, then that's for the four metallic and non-metallic characteristics. It's actually, if I go back to the ionization energy, it's the exact opposite of ionization energy when we are talking about metallic characteristics. Okay, metallic characteristic increases from top to bottom and decreases from left to right. It's the exact opposite, okay, of ionization energy. Okay, that's for metallic characteristic. As you could see here, metallic characteristic is the exact opposite of ionization energy. Okay, metallic characteristics decreases from left to right, increases from top to bottom. Look at francium, it's the highest metal. Okay, it's the metal with the highest metallic characteristics. Okay, all right. Now, then we talked about ionization energy and we talked about metallic characteristics. Now let's talk about the atomic size. Okay, as we go on the same period on the periodic table, the atomic size decreases. Okay, then why the atomic size decreases across the same period? If you look at the periodic table here, as we move from left to right, what is increasing? It's the number of protons increasing. Look at iron 26, cobalt 27. Then it has bigger number of protons, or the atomic number increases. When the atomic number increases, as we move from left to right, that means there is going to be a higher pull between the nucleus and the electron. Okay, that's why the size shrinks. Okay, that's why as we go from left to right on the same period, the atomic size decreases. Whereas as we move from top to bottom, the atomic size increases. Why? Because the principal energy level increases. Look, from 1 to 2 to 3 to 4, 5, and 7. That means we get further and further away from the nucleus, and that's why the size of the atom increases. That's the reason for atomic size. Then one more time, for atomic size, within the same period, as we move from left to right, on the same period, the atomic size decreases. Why? Because the number of protons, or the atomic number, increases. There is a higher pull between the nucleus and those electrons, those valence shell electrons. Whereas as we go down the group, the atomic size increases. Why? Because the principal energy level, N, increases, which means we get further and further away from the nucleus. That's why the size gets larger and larger. This was the end of chapter 9.